Welcome. In this video, we're going to look at some substitution methods for solving differential equations. This stage, or we use these particular methods at a time when, in fact, we get to the point where our equations are even linear equations, be it, or the equations don't appear to be separable. That is when these types of substitution methods come to be very useful. So I'll explain. Well, best is to start with an example, for instance. Here you'll see an example of this differential equation, and we note that basically, if you look at this differential equation, is a first-order nonlinear differential equation. Problem is, it is not separable. And so far, we've learned these two methods. Either an equation is separable, we can try to solve it, or it's a linear differential equation and we use the method of integrating factor. So here we're stuck, as there doesn't seem to be much we can do. However, there is something that can be done, and that is basically if we go for a substitution and let, for instance, a new variable v equal x plus y plus 3, okay, and then dv dx, okay, is just the derivative of x is 1 with respect to x, the derivative of y is dy dx, and 3 is a constant, so it's just 0. So now this implies that, of course, dy dx, okay, is dv dx minus 1. So with this, okay, and this, we're now able to change this differential equation into this one. So now if you look at the equation, what's magically happened is this equation is now separable. So we can what I mean by that is, okay, so you can see there, and because it's separable, now I can integrate both sides. And basically here, the easily integrated to tan inverse of v equals x plus a constant. So we've actually done this part, so therefore, and of course then v is tan of x plus c. Now we of course go back and change the variables, so back to x plus y plus 3 equals tan of x plus c. And of course now we have our final solution, and there it is. So as you can see, by making this very nice little substitution, we were able to actually convert an equation that is not separable into one that is separable and actually go on and solve it. So now what we're going to do is we're going to look at a recipe of a family of differential equations that can actually be solved with a similar substitution. Let me show you what I mean. So if we look at this family of equations, dy dx, where dy dx is a function of ax plus by plus c, this is a linear combination of x, y, and a constant. Such equations with a substitution, with this substitution, v equals ax plus by plus c, we can actually solve such equations. Now let me just, this one here, you saw that a is 1, b is 1, and c is 3. But I want to try to give you some quick examples of the type of equations we can solve using this method, this substitution. And here's one example. So dy dx equals, for instance, sine of, okay, 2x minus 4y, okay, or sorry, that's 2, okay, 2x minus 4y. So in this case, the substitution v equals 2x minus 4y should work. Okay, it should convert this into a separable differential equation. Another example could be, for instance, dy dx is equal to the exponential of 3x plus 2y minus 1. And the substitution here would be v equals 3x plus 2y minus 1. So that substitution should work. So I'll stop here, and we'll continue in the next video with a different type of substitution method, another family actually of a substitution method. Thanks so much.